It's unfortunate that this lecture happened today when so many of us are missing, because we finally get to the good stuff. Okay, we've been talking about the basics of waves and just the fundamentals, and now we get to talk about the really interesting things: Doppler shift, Mach cones, beats. Doppler shift, you're familiar with, I believe. I think what you hear when this race car goes by is the Doppler shift. Even if you had your eyes closed and you were at that track, you would know when each of those cars went racing past you. You'd hear that. That's the Doppler shift that we'll be talking about today. Before we get started, why don't we have a prayer? If you'll allow me, I'll offer that. Our dear, kind Heavenly Father, at this Thanksgiving season, we bow our heads in gratitude for the many, many countless blessings which have been poured out upon our heads. We're especially grateful to be here at BYU and to have the opportunity to associate one with another, to learn one from another, and to serve one another. We are grateful for the guidance that we receive from thy prophet and from the other general authorities that work with him. We ask a blessing upon President Nelson, that he might be kept in good health, that he might be strengthened. We are grateful for our families, and we ask a blessing especially upon these young people as they travel to be with their families, that they might do so in safety, that they might be able to stay alert, and that their transportation will function. We ask a blessing upon those who are not able to return home to their families, that they might feel of their family's love, and that they might be comforted and lifted up at this holiday season. We ask now that we might be able to open our minds and understand the things which are being taught this day. And this we pray in the name of Jesus Christ. Amen. Okay, come on in. So before we talk about these really fun topics, let's give you some help on the tutorial. Now, you will have noticed that because tomorrow is a holiday, the tutorial homework is not due until the Wednesday when you get back. But if I were you, I'd get it done, get it out of the way, just so it's not hanging over your heads during the holiday. Now, you remember that during the tutorial, we investigated the reflection off of a fixed end. And then right at the end of the tutorial, we had a demonstration of what it looked like for a free end. And we found that those were very, very different. For a fixed end, if I send in a pulse on top, it inverts, it flips upside down, and it comes back on the bottom. Now, the mathematics of that, meeting the boundary and kind of disappearing and then coming out on the bottom, is very messy. Again, it involves a differential equation, which means we got to understand calculus. And we swore an oath to each other that we wouldn't use calculus, okay? But there's another way that you learned in that tutorial that makes this very, very simple. When this comes in, that point right there at the boundary doesn't move. And the other thing we know is that it comes in on top and it comes out on bottom. Well, how can we make that happen without the fancy mathematics? Well, what we do is we pretend that this wire that's hooked to the wall doesn't end at the wall, that it goes behind the wall where the spiders live, okay, forever. And behind that wall, we imagine that there's another pulse coming the other way. And this is a very, very special pulse. We want this pulse to be just the right shape and just the right position so that this point right there at the wall never moves. And the way we do that is we take this pulse and we reflect it across the boundary and we invert it. Okay, so we reflect it across the boundary and invert it. Now what that does is it ensures that this point never moves. When this point reaches the boundary, so does this one, and they cancel. When this point reaches the boundary, so does this one, and they cancel. This point never moves. So let's look what happens as the pulse meets the wall. If I, come on, I'm asking you to move. Okay, there we go. If I move this pulse, we call this the incident pulse, and we call this the reflected pulse. If I move the incident pulse 2 squares to the right, well, this pulse is on the same wire with the same tension, same mass density, so it has the same speed. So it's going to go 2 squares to the left. And now I use superposition. Superposition is a fancy name for add them up, okay? We call it superposition just to scare people. Okay, right here I have plus 3/4 and minus 3/4. That's going to give me nothing. Right here I have 1.5 and 0. That's going to give me 1.5. This is going to be 3 and 0. That's 3. This is going to be 0. And so that's what the wire is going to look like when it meets that wall. It crumples in the front. Well, now let's go further. Let's let this thing go 4 squares to the right, and this one's going to go 4 squares to the left. Well, now we just add them up. And again, we don't care what happens over here. That's where the spiders are. We just care what happens in the daylight. So here I've got 2.25 and negative 2.25. That's 0. Here I've got 3 and negative 1.5. That's 1.5. And then I get down to 0 here. Well, let's go carefully. That's 1.5 and negative 3/4. That's 3/4. And then we're at 0. So now we see that that's really crumpled. Well, now let's move 6 squares to the right. And this one goes 6 squares to the left. And now I've got 1.5 and negative 1.5. And then I've got 0 and negative 3. And so you see that mostly it's the reflected pulse, but it's missing a little bit on the tail end. Okay, and then we go 8 squares to the right, 8 squares to the left, and now you see that we have lost the incident pulse and we just have the reflected pulse, and it comes out. Okay, so what we found with that simple make-believe process was that that pulse started with this shape, and then it came in and crumpled in the front. It almost disappeared, and then it came out upside down with the tail missing, and then it came inverted and flipped. Okay. Now, it's important to note that this pulse doesn't bounce off the wall like most things, like a rubber ball, for instance. Okay, it's more like a snake where the leading edge remains the leading edge. If I call this the leading edge because it's in front of the charge and I paint it blue, when I get the reflection off of that wall, the blue side, the leading edge, is still leading the charge. Now, that's not what happens when, say, a rubber ball hits the wall. If I paint this side of the ball blue and this side red, the blue side is leading the charge, but because the whole ball bounces at once, the red part is leading the charge coming away. So what's happening here is the front part of this pulse is bouncing off the wall at the same time that the back end of the pulse is still going towards the wall. It kind of turns around like a snake. See if your neighbor's on the bus. If not, just slap them away.
Oh, I actually could use that.
You can barely reach your neighbor today. There's so much empty space. Okay. Now, your homework concentrates on reflection off of a free end. And a truly free end would have a massless ring sliding on a frictionless post here. And you know those things don't exist, but we can have a ring that's very, very light on a very, very slippery post, and we can approximate that. And what we find is that the pulse comes in, and instead of flipping, it comes back on the same side. And when it meets that boundary, my amplitude actually doubles. Now, the way we understand that without the fancy math is, again, we make believe that this wire goes behind the wall or behind the boundary. And this time, what we do is we just take the original incident pulse and reflect it, but we don't invert it. We just reflect it. And now you see that when these two meet right here, I get something that is twice the amplitude. Now, you've probably witnessed this last time you were at Cancun. You see a water wave coming into some kind of a seawall. And when it gets to the seawall, it splashes up. Okay, it splashes up. Now, remember last day, I talked about a pulse traveling through a wire or a string or a rope. As the model we used was a bunch of football players that were holding each other's hands, okay? And it was a bad example because we just lost the game, okay? But each of those football players jumps up to let the pulse through. And in the process, lifts his neighbor, who lifts his neighbor, who lifts his neighbor. Now, with a fixed end, we eventually get to Fred, tight end, and instead of another football player there, he's holding on to the wall, okay, the door handle. And he tries to lift up the room, and it doesn't go. So instead of lifting up the room, he pulls himself down, and that's what brings that pulse reflected on the bottom, okay? Now, on the other hand, with a free end, we got those football players pulling each other up, and we get to Fred. He's expecting to pull up a football player, and there's nothing there. And so it's kind of like when you're pulling on your shoelaces and they break. Okay? And so we get twice the amplitude. See if that makes sense, if that speaks to your neighbor's soul. Otherwise, you know what to do. Okay. Now, what we have here is a long spring, and it's free to slide on this bar that's slippery. And I'm going to send down a pulse, and the pulse that I'm going to send down is too small to knock down these cups, okay? and the reflection is going to come back on the same side. But watch what happens to this cup right here when the pulse reflects. Oh, that's just amazing. Things don't work like that in biology. Okay. Okay. Now, the hardest part of that tutorial homework deals with this boundary condition on the free end. And so let's talk about that. Again, there's two conditions for a free end, a truly free end. That little ring or pulley or whatever you want to model it as has to be massless. And second of all, this rod has to be frictionless. Now, I know that if it's massless, use Newton's second law, F net equals ma. Okay. If it has no mass, we don't care what the acceleration is. When you multiply it by 0, that's 0. That means that this little ring, this little connecting device right there, has to always have a 0 net force. Now, if you think about it, there's only two forces acting on it. There's the rod pulling on it to the right, and there's the string pulling on it to the left. And the thing about a frictionless rod is that it can only exert a normal force. There's no friction. The only thing left is a normal force. And what direction would a normal force point? Tell your neighbor. Okay, I hope you said normal, which means perpendicular, okay, in math speak. Perpendicular to the rod. Now, if the net force is 0, that means the pull by that string has to cancel that perpendicular force. And that means if I try to make the wire go like this, I have violated Newton's second law. Now, there are some traffic laws you can violate, but Newton's second law you can't. And so that's just going to instantly go to 90 degrees. And if I try to bring that down there, before you can blink, before you can even think, it's going to go like that. And we call that the boundary condition. It must always come into that boundary at 90 degrees. Now, what you'll find in that tutorial homework is that when you bring in one of those pointy pulses and do the math, the superposition, you find that it doesn't come in at 90 degrees always. And what that tells you is that you've never seen one of those pointy pulses in real life. Nature will not let it happen, okay? We use those pointy pulses in our problems because they're easy to add up the two pulses together. They're easy to work problems with. But we have to recognize that in real life, they come in rounded like we saw in the simulation. Okay, are there questions on that tutorial homework before we go to the fun stuff?
There was one part where it asked about drawing a free body diagram when the fastest ring is farthest from equilibrium. I wasn't really sure what that would look like. I know that the forces have to be balanced. At 90 degrees, I guess.
Right, and it just furthest from equilibrium. Remember, equilibrium is its happy place, and so that would be when the two are meeting, the incident and the reflected, and so it would be the furthest away from the happy place, or 2 times the amplitude. But it would come in at 90 degrees, like you mentioned.
So it looks like it would look like the free body diagram at equilibrium, but be double the force per volt.
Oh, if you take into account the fact that you've stretched the wire a little bit, it'll be bigger. But the point we were trying to get was that it's still 90 degrees to the left and 90 degrees to the right. That, yeah. Okay. That's the boundary condition. Okay, let's That's what fire trucks sound like in Europe. So let's listen to that again. Can you tell when it went past you? If it had a high, that was the Doppler shift. Now, the Doppler shift, the way I was taught the Doppler shift was through equations. Lots of equations and lots of algebra. And that's the way I thought it was supposed to be taught. And that's the way I taught it for a long time. And then I got married to my dear wife. And right after we got married, I was at her home when her teenage sister came home with one of her friends. And they were learning the Doppler shift in their high school physics class. And they were having trouble with it. And my sister-in-law, Lori, said, "This is Greg. He's a geek. He can help us." And so we sat down at the kitchen table and I tried to teach them the way I was taught through equations. And they got more and more frustrated. And my sister-in-law can be a little mean when she's frustrated. And I could see that it wasn't going anywhere. So finally I said, "Ladies, let's go to the bathroom." So we got up, we walked down the hall to the bathroom. I filled up the tub. We knelt down in front of that tub, and I started tapping on the water. And that's the way I taught them the Doppler shift. And that's the way I'm going to teach you. So people, stand up. Let's go to the bathroom. No. We're going to use our imagination. Oh, I love hearing the lonesome wail of the train whistle as the frequency of the wave changes due to the Doppler effect. That's what they're saying, not "Let's rob that train." Okay. What we're going to do is we're going to use our imagination and imagine that we are looking down on a pond. And in the middle of that pond, there's a skeeter bug. His name is Bob. And Bob likes him some music. Okay. Well, not really music, it's country and western. Okay. And when Bob is listening to music, he stomps. He stomps to the music. And every time he stomps, he sends out a ripple that goes in all directions. So he stomps and he stomps and he stomps and he stomps and he stomps. Okay? And he makes those ripples. Now, if I were to put a leaf, right here on the pond and a leaf right there on the pond, those leaves would both bounce up at the same frequency that Bob was bouncing, was stomping rather. And I know that because these ripples go out at the same speed in all directions. Okay. So whenever he creates a ripple, it moves over to the leaf and makes it jump up. Does that make sense? Okay. Now, it turns out that Bob has a brother, Billy Bob, and he likes to move. And so Billy Bob stomps and slides, stomps and slides, stomps and slides. Okay. And every time he stomps, he moves a little bit into the ripple that he has just made. Now, you see that the effect of this, because he's moving to the right, is that these lines, you should see that as the crest of our pulses. This would be a little hill of water, maybe a millimeter high. And this would be another hill of water. And this would be another hill of water, and a hill of water, hill of water. Okay. And this circle here, the biggest one, that is the ripple that Billy Bob made when he was right there in the middle of that circle. And this circle here is the one that he made when he stomped right there. And that's in the middle of that circle. And this one is the one he made when he was right there in the middle of that circle. And here he's about to stomp again. Okay. Now, if instead of putting a leaf here, if instead we think of these as sound waves, and these being the crests of the sound waves, and we're listening to that, we're letting them assault our eardrum, well, what we see is that here the wavelength from crest to crest has been compressed because of Billy Bob's motion. Okay? And if I look at that wave equation, the speed stays the same. If this is sound, that's 343 meters per second. But if the wavelength has gotten compressed, the frequency has to get bigger, higher. And that's why you hear that high note as the race car is coming towards you. On the other side, when you're back here and Billy Bob's going away from you, again, if this is sound, what we find is that the wavelength from crest to crest is stretched out, is longer than it normally would be if the source was not moving. And if I look at that wave equation, well, if this gets bigger and the speed stays 343 meters per second, the frequency has to get lower, okay, lower. And so if you're in front of the motion, you get that shift up. And if you're behind the motion, if it's going away from you, you get a shift down. That's what we mean by Doppler shift. It's a shift in frequency. Okay. If this source is making a constant 400 hertz, then you're going to hear something higher than 400 hertz here, something lower than 400 hertz there. See if your neighbor's on the bus there. Okay. I show this picture only because it came out of Paul Hewitt's textbook. I have a textbook for the conceptual physics class. It's not the textbook you're using. It's another textbook. And my textbook is the second best selling textbook in America. That's what I told, no. That's what I told my father when he was alive. What I didn't tell him was that I had like 2% of the market share, and Paul Hewitt had 98%. He's got his own island because he could make really funny cartoons. Anyway, I did this for Paul. Okay. With that textbook, I think I made about $2.50 an hour writing that. So you gotta love it. Okay. Let's see if we can answer this question here. A stationary source, like a whistle, produces waves, let's say at 400 hertz, and you measure their speed, wavelength, and period or frequency. If you know one, you know the other. If the same source is moving towards you and you make the same measurements, what changes and how? The speed, would you measure something faster, slower, or the same? Shout it out. The same. The wavelength, longer, shorter, the same? Shorter. Okay. The period, the time it takes for a wavelength to go past. Shout it out. Shorter. And the frequency? Higher. Good. Let's play this one more time. But this time the source is moving away from you. Again, the speed, same. Wavelength, longer. Period, longer. Frequency, lower. Okay, you've got it. Now I'm going to demonstrate this this effect for you. Okay. The people in the front are going to be able to detect it better than everyone else. My point with that was that there was no possible way that we were going to get this old man moving fast enough to actually demonstrate the Doppler shift, okay? In order for you to be able to hear that shift, I would have to be going at some appreciable fraction of the speed of sound. The speed of sound, 700 miles an hour. Was I close to 700 miles an hour? Yeah, okay, thank you. That's very kind. Okay. There is a way that we could get me going that fast, but it's going to hurt at the end. The Doppler effect. Now, I'm going to probably hurt somebody, but I don't mean to. Okay. You should hear something different when it's coming towards you than when it's going away from you. Do you hear it? Okay. In Montana, I had the buzzer on the end of a long pole, and I would go, I bless you, I bless you, I bless you. I can do that because Pope Francis is my uncle. He's not really. He's Catholic. So anyway, we also have this little ball that we can get buzzing. Okay, do you hear a different frequency when it's going one way or the other? Let's just stop that. Okay. Now, what would this sound like? We talked a moment ago about the source moving, but what if the source isn't moving? What if the source is stationary, like that whistle? And you're moving at some appreciable, let's say you're in a car and you're moving at some appreciable speed, like 30 miles an hour towards that whistle. Tell your neighbor what that's going to sound like.
You know, get more high pitched.
Yeah, like you're going.
It sounds it plays it back higher pitched and similar to the get.
Okay. So let's say the whistle is playing middle C, the note middle C. What are you going to hear? Something higher than middle C? My question is, as you get closer and closer to that whistle, is the frequency that you hear going to go higher and higher or stay the same? Talk to your neighbor. Higher and higher or stay the same? Okay, we're not going to use our clickers. We're just going to use our hands. How many say it's going to go higher and higher? How many say it's going to stay the same? Okay, stay the same wins. The shift up from middle C depends on how fast you're going towards the source or how fast the source is coming towards you. If you've got cruise control on, you're always going 30 miles an hour, you're always going to hear the same shift. Maybe it's D instead of C, but it's going to stay D. What is going to change as you get closer and closer is the volume. When you're far away, it's going to be D, 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 D. Okay? It gets louder and louder, but not higher and higher. The volume is how hard those wavefronts are assaulting your eardrum. The frequency is how many times they assault your eardrum each second. Those are very, very different things, very different things. Now, this is an old exam question, and I bet you wish that it was on yours. You've got this child swinging on a tire swing from A to E. And we've got this stationary whistle here that's playing some note. And we want to know at which position the child's going to hear the highest frequency for the sound of the whistle. And our choices are at B moving towards C, at C moving towards D, at D moving towards E, or at E. I'll get you started here. Hold on. Now you can click. Just think of all those people on the beach in Cancun. They are missing these attendance points. Don't you feel sad for them? Okay. Get your vote in. Let's not miss out on those attendance points. Last call.
You're slowing down.
Oh, we don't know. We don't know. Well, I'm glad we're having this discussion. The shift is going to be greatest when the relative velocity is greatest. And we know from earlier in the semester that on this swing, she's going to be going the very fastest at C, okay? Because she was speeding up downhill, she's going to be slowing down uphill, and so the answer is going to be at point C, moving towards D. Okay? Everyone, are there questions on that? Yes.
So doesn't it start slowing down at C? Which way does it go? Yeah.
Let's say that right at noon, you change from speeding up to slowing down, okay? And you've had your foot on the gas all the way up till noon, and you got your foot on the brake immediately after noon. You're going the very fastest at noon when you're taking the foot off the gas and reaching for the brake. Okay. Okay. The key concept here is that louder is very different than higher. Middle C on a piano moving at constant speed does not sound higher and higher as it gets closer and closer. It just sounds louder and louder as it gets closer and closer. Okay. Now, let's talk about Mach cones. This is truly fun stuff. Truly fun stuff. And to introduce that, let's go back to the pond where we have another brother, and this is Billy Joe Bob. Okay, Billy Joe Bob also likes to stomp to some music, but he's faster than Bob or Billy Bob. Okay, much faster. Indeed, if I look at him moving, there he is moving as he makes his ripples. How fast would you say Billy Bob is relative to the speed of the ripples? Almost as fast. Almost as fast. He is going almost the same speed as the ripples that he is creating on that pond. And we believe in superposition. And if each one of these ripples is 1 millimeter high, what does Billy Joe Bob see right in front of his nose? A wall of water. Okay. Now, you know that's not what's going to happen, and that's because there's some nonlinear effects that are going to keep those things from actually stacking up on each other with water. But with sound waves, with compression regions in sound waves, they stack up. And so if this was instead of a skeeter bug on a pond, if this was, say, a jet, something like that, then if it was going almost the speed of sound, all of the sound that it had created all afternoon is going to be bunched up right in front of that plane. And that's what we talk about breaking the sound barrier. Now, when I was young, when I was in high school, I thought the sound barrier was a psychological barrier. Back then, when I was alive, no person could run a 4-minute mile. And we all just thought that was impossible. And so that was a barrier, a psychological barrier. But this is not like that. This is a physical barrier. If any of you have watched the movie The Right Stuff, you know, as they're trying to break through that sound barrier the first time, their planes rattling apart, you know, because they've got these very high pressure regions there. Now, these days we can actually go faster than sound. We're not allowed to a lot of the time because it wreaks havoc on your windows and things like that. But we have jets that can go faster than sound. And so if we look at that, how much faster than, if this is a sound pulse, how much faster than sound is this plane here? Yeah, about 30% faster. And you see that as that plane continues to make sound, the sound, well, I just made beats like stomping on the water. And in that case, I would superimpose it here and here and here and here and here and here. But if this plane were making continuous noise of all different frequencies, instead of just having a few points that would be on top of each other, you would have a pressure front that looked like this. And it only looks like that on a flat screen. In three-dimensional space, what does that look like? A cone, a cone. And we call that a Mach cone. And that's after Ernst Mach, German scientist. Okay? Now, that Mach cone, let's think about it for a moment. If I have two planes, one going Mach 2 and the other going Mach 5, whoa, what does that mean, Greg? What does it mean to go Mach 2? If you're going Mach 2, how fast are you going? Anyone? Brave soul? Raise your hand. No one?
Does that mean you'd be ahead of two of the circles?
You what?
You'd be ahead of like two of the circles? One.
Ah, you would be twice as far ahead as the sound. And so we say that Mach 2 is twice the speed of sound. If the speed of sound is 343 meters per second on a nice clear spring day, then Mach 2 would be twice that, or 686 meters per second. The speed of sound is roughly 700 miles per hour. Mach 2 would be 1,400 miles per hour. Okay?
And like on a regular temperature, if you were in a colder temperature, would it be easier to go Mach?
Yes, very good. Remember, we found that the temperature of sound, the temperature of the air affects the speed of sound. It goes slower when it gets colder. And so, indeed, it would be easier to break the sound barrier on a cold day. Very good. Very good. Now, let's go back to those two planes, the Mach 2 and the Mach 5. Which one of those is going to have a fat Mach cone and which one's going to have a skinny Mach cone? Talk to your neighbor. Which is going to be which? Okay. I hope you can see that if the plane is Mach 5, it's getting out way, way ahead of those little ripples. And so that's going to be a very narrow Mach cone. And the Mach 2 is going to be the fatter Mach cone. And indeed, if we define this angle, we're going to make a right triangle there. And we're going to define this angle, actually a half angle of my Mach cone. And that angle, theta, determines, just by knowing that angle, I can tell you how fast that plane is going. That angle gives me all the information I need about the speed of that plane. Let me show you how. We're just going to do a little bit of trigonometry, not much. But if we think of this right triangle here, this is the hypotenuse of the triangle. And this is the side opposite my Mach cone angle, theta. Now, if I think about this line here, the hypotenuse, that's how far the plane has traveled in the time that I was watching. It went from here to here in the time that I was looking at it. Does that make sense? On the other hand, the sound that was made when the plane was here went out in all directions. And it got this far by the time the plane got this far. So this is going to be the speed of sound times the time we were looking. And this would be the speed of the plane during that time. Now, I know that the sine of that angle is the opposite side divided by the hypotenuse. This divided by that. Well, that's the speed of sound times delta t. That's the speed of the plane times delta t. The delta t cancels out. And what I have there is 1 over the Mach number. If the Mach number is the speed of the plane divided by the speed of sound divided by the speed of plane is 1 over the Mach number. 1 over the Mach number. Does that make sense? Check on your neighbor. Now, a warning. On the final exam, if you have a Mach cone problem, a supersonic plane problem, if you try to solve that problem without that equation right there, just give yourself a 0 on that problem, because that's what you're going to get, okay? That equation is what governs a Mach cone problem. Now, let's talk about this picture here. We call that a vapor cone there. And the question is, what causes that? Well, I have here let me turn up the lights here. Turn up the lights. Okay. We're going to create a cloud. I've just got a little alcohol here. I got it cleared with the administration. Besides, it's isopropyl. So I'm just going to put a little in here. And then I'm going to increase the pressure in the bottle. And then I'm going to lower the pressure. And I've got a cloud. I can make the cloud go away. I can make it come back. It's magic. Okay. Now, what is happening there? Well, we know then from our chemistry class that if we lower the pressure of a gas really fast, we cool it. We suddenly lower its temperature. Now, you may have experienced this if you were ever playing with a fire extinguisher. As you fire that fire extinguisher, you are essentially expanding the gas. You're lowering the pressure and letting the gas expand. And in the process, the bottom of that fire extinguisher gets all frosty, doesn't it? Well, maybe you didn't do that because you're good people, okay? my daughter's 16th birthday. Her friends talked me into climbing into a professional clown suit and showing up on the front steps of the high school with a fire extinguisher, and I had floppy feet and everything. And anyway, she came in and I followed her all the way down the hall with this fire extinguisher, firing it at different students. And this is Heidi, she's my girlfriend. And anyway, totally humiliation. Anyway, we got into the we got into her German class, and I accidentally hit Frau Schmidt, and then her high school is now a clown-free zone. I'm responsible for that. That's not going to be on the test. Okay. Now, what's happening with that plane is that we've got what's called a sonic boom. Now, I used to believe, again, when I was young, that the sonic boom happened when you crash through the sound barrier. And we had sonic booms all the time at my house because I went to high school on Guam, and Guam, my house was just down the island from Anderson Air Force Base during the Vietnam War. And we had these bombing missions leaving every half hour and these fighter jets going to support the mission. And I thought that I was just the luckiest kid in the world because they were always punching through that sound barrier right at my house. Well, the truth is, once that plane is going faster than the speed of sound, it drags this Mach cone with it wherever it goes. I was a lucky kid, and then the kid down the street was a lucky kid, and every kid on the island was a lucky kid when it was their turn, okay? It just follows along. And it's not really a sonic boom, it's a sonic ba-boom, because there's a high pressure shock wave in the front, and then there's a low pressure shock wave, kind of like an eddy that happens behind a rock in a stream. And so the atmospheric pressure, if that's what atmospheric pressure is, this part of the boom pushes your eardrum in, and this part pulls it back out. Now, changing that pressure from high to low is what drops the temperature, and that causes the gas, if it's got enough moisture in it, to condense into a cloud so that you can visualize it. Now, here's a video of a plane going past a Navy ship, and as it dips down close to the ocean where the air is humid, we get one of these vapor clouds. Whoa. So I could show you that video and ask you how fast that plane was going. You'd take out your protractor, measure that angle, and figure it out. So here are some other examples of those vapor clouds. Notice that they're happening near the engines where the sound is being made, and also by the cockpit where we've got some turbulence. That one's just messy. That one's nice and clean. Whoops. Yeah, I want to point out that this one was very famous on the internet, just showing that there are other ways that we can drop the temperature due to a dropping of the pressure. And it's pretty clear, I think, to everyone that that plane's not going Mach 2. Okay. So this is the type of problem you'll have on your homework and indeed on the exam. You look directly overhead and you see a plane exactly 1 kilometer above the ground. It's traveling Mach 2. How far will the plane travel before you hear the sonic boom? Ba-boom, okay? Well, there you are. There's the plane 1 kilometer above you, and there's the Mach cone that it's trailing behind it. And it goes down the road, and when it finally gets far enough, the Mach cone reaches your ear. And the question is, how far has it gone before you hear that? Now, here's a simple answer. Well, if the sound could go 1 kilometer and it's going twice the speed of sound, it must have gone 2 kilometers. Wrong or sick and wrong? Sick and wrong. What was wrong with that? I didn't use the equation. I didn't use the equation. And it turns out the answer is not 2 kilometers. I'll explain why in a moment. It's not 2 kilometers. So let's use the equation. I'm looking for that angle there. And I know that the sine of that angle is 1 over the Mach number. We're told the Mach number is 2. That means the sine of that angle is 1/2. Well, what angle has a sine that's 1/2? Do you know? Geeks know. It's 30 degrees. Do any of you watch The Big Bang Theory? Have any of you, one person in the whole place? Oh, 2 people. Okay. Then I'm not even going to tell you the joke because you wouldn't appreciate it. But the sine of 30 degrees is exactly 1/2. Exactly 1/2. And so that means this angle here is going to be 30 degrees. Now, what you would do on your calculator is you would plug in 1/2, 0.5, and hit the inverse sine button, okay? And you'd get 30 degrees. Now, I know that the tangent of this angle is going to be the opposite side, which I know, divided by the adjacent side, which I'm looking for. And so I can solve for this x, this distance that it travels, by just cross multiplying, and I get it's 1 kilometer divided by the tangent of 30 degrees. And that gives me 1.7 kilometers. And that's not 2 kilometers. Well, why didn't the simple answer work, Greg? And that's because when this Mach cone assaults your ear, it's not sound that came from the plane when it was here. It's sound that came from the plane when it was back here, perpendicular to the Mach cone. Okay? And that's why the simple answer gives you the wrong answer. Check that your neighbor's on the bus and could work these problems on the homework and the exam. Okay, so you're in a plane going Mach 2, and you're the pilot, and you turn to your co-pilot and talk to that person. What do they hear? They hear the same thing they'd hear in your front room. I'm just messing with your head. The air's not moving in the cockpit. Sorry. Let's talk about beats. Let me give you an example here. I have 2 signal generators. And that's 500 hertz. That's 504 hertz. And if I play them together, you hear the wah-wahs? Wah, 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 wah. Okay. Now, if I change this one to 502 hertz, I slow them down. If I make this 506, okay, enough of that. I can also make those wah-wahs with these 2 tuning forks. Now, these tuning forks came from the factory identical, but then we put this little extra mass on the back of this tuning fork. Is that extra mass going to speed this oscillation up or slow it down? Shout it out. Slow it down. So that's going to give me a lower frequency over here. Now, that's important in your homework because you've got a homework problem where you've got two tuning forks and you put a little bit of clay on one of them. And everyone always asks me, well, does that make it go higher or lower? Well, it's extra mass, makes it go slower. More mass is harder to move. Believe me, I know. Okay? Now, that's what that sounds like. That's what that sounds like if I make them both go together. You hear the wah-wahs? Okay. Okay. Now, what's going on there? It's superposition. Both waves, the wave from this tuning fork and the wave from this tuning fork, is traveling across to your eardrum at the same speed, 343 meters per second. But because they have different frequencies slightly, this one was 440 and this one's 438. If they have different frequency but the same speed, by the wave equation, they've got different wavelength. And the wavelength is the distance from crest to crest, or from compressed region to rarefied region. These are the compressions, the wavefronts, the crest of our sinusoidal wave. And you see, as these move across the room at the same speed, they do so such that some of the time I have the compressed region of one of the waves lining up with the compressed region of the other. And other times I have the compressed region of one of the waves lining up with the rarefication region of the other. And so here we say they destructively interfere, and here we say they constructively interfere. Now, I've got a little simulation here. What I have are two waves, one coming from the left, one coming from the right, and they have slightly different wavelengths. You see the distance from this crest to that crest is longer than the distance from this crest to that crest. I have a little dot, and that dot might represent some piece of your eardrum as these two waves are interfering with each other. And I want you to just watch what happens as they meet the dot. Oh, it goes on forever. Okay. Glad that's over with. What we find, if we look carefully, is that when we take two waves that have slightly different frequencies, if this was a time of 1 second, this would be a 10 hertz, 10 oscillations per second wave. And this would be a 12 hertz wave. And what you see is that we get points where a trough meets a trough, and we get a super trough. And we get places where a crest meets a trough, and it cancels out. And so what we end up with is a wah, wah. And it's not a coincidence that I get two of these beats, we call them, 2 beats per second, when the difference in my frequency is 2 hertz. Okay, and that gives us this formula for beats. It's the difference between the two frequencies. The difference between those frequencies. And those absolute value signs present some complications that you'll see in the homework. And that is, we never know which source is higher and which one is lower. We just know that they're different by a certain amount. If I'm hearing 5 beats per second, I know one of the sources has a frequency that's 5 hertz higher than the other. Now, there are some demos that I don't have here. I wasn't able to bring them with me to Utah. And I've tried to duplicate them. I have been to every Home Depot and every Lowe's to try to duplicate these, and I haven't been able to yet. So you're going to have to watch a video. This is Montana. It's cold there, always. Now, those of you that go to church, you know that the organ makes high frequency noises and low frequency noises, the noises we call music. And it's the long pipes that make the low notes. Well, I've got two organ pipes here that are slightly different length, and so that means they're going to make, through a process we'll understand on Monday when we talk about longitudinal standing waves, it's going to make two slightly different frequencies. And I'm going to sound them both at the same time, and you should hear beats. Now, I want you to appreciate something. Just for a moment, think about all the old fat professors that have had their lips around that in the last 40 years. Okay, there's nothing I won't do for you people. I love you, okay? Okay, you heard the wah-wahs? Okay, now, if you can do a demo with fire, why wouldn't you? Okay. Now these Bunsen burners are there just to make white noise, to make frequencies at all different frequencies, to sputter. If I had a different way of making a sputtering sound, I probably wouldn't. I'd probably still use the flame. That source of white noise creates all these different frequencies, and we're going to find on Monday that there's one frequency that wants to resonate with this tube, this length of tube. It's this frequency. Okay? Now we're going to find on Monday that that frequency that resonates, that makes a loud booming sound, is determined by the length of the tube. So if I have another tube that is slightly different length, it's going to make a slightly different frequency. And so if I sound them together, why would anyone want to teach math? Okay. You're singing along with Celine Dion on the car radio as she sings a long, steady note. You know that you are a little off key because you are hearing beats at 2 hertz. Are you singing a little too high, a little too low, or can't you tell? Yeah, you can't tell. Okay. You can't tell, you just know that you're off by 2. Let's look at this homework problem. A guitar string produces 4 beats per second when played simultaneously with a 250 hertz tuning fork, and 9 beats per second when played with the 255 hertz tuning fork. What is the actual frequency of the guitar string? Okay, so let's go to the board. This is where those absolute value signs get in our way. I know that the frequency of the guitar, when I play it with the 250 hertz tuning fork, gives me 4 beats. That tells me that the frequency of the guitar has to be equal to 250 hertz plus or minus 4 hertz. Well, that doesn't tell me what the frequency of the guitar is. It just tells me that it's either 254 hertz or 246 hertz, but not which one. So I need that second experiment. And by the second experiment, I know that the frequency of the guitar is going to be equal to 255 hertz plus or minus 9 hertz. Now, if I add 9 hertz, that's going to give me 264 hertz. And if I subtract 9 hertz, that's going to give me 246 hertz. It's the same guitar string in both experiments. And so the only answer, my dear Watson, is the one that's consistent. Okay? Check that your neighbor is on the bus. Okay. We have one more thing to do. This is just a little bit of market research. I want to ask you, which of these concepts was most difficult to understand? If I was to work on making it better for one of these concepts, which would it be? Okay, last call. Okay. Oh, Mach Cones. Okay, drive safely if you're driving. Stay warm. Hug your family.